Calculus! We are in AP Calculus 11-4. Ben, Rochelle, we miss you. Era was going to teach a lesson today, but it's awkward teaching a lesson to no students, so I will teach it to one student, which is, in my opinion, even more awkward, but let's go ahead and do this anyway. Today's date is Friday, March 22nd. I am running a bunch of stuff in the background, so hopefully it is not degrading the quality of the video. So today we're finally doing our second type of 3D things, 3D graphs with calculus. Let's go ahead and see two different functions that are graphed. And unlike the notes error, I'm going to make my first graph of f of x nice and straight. So some straight linear graph, and since I have technology, I'm going to make it look really nice. And then some other function. I'm going to do my other function in red that comes down something like that. Some maybe quadratic, it might be polynomial, well definitely polynomial since quadratic is a subtype of polynomial function that looks like that. Notice that they intersect here at AB. So I'm going to say right here is A, right here is B. I have the x coordinates of their intersection. What I'm going to do is I'm going to revolve this area, so you can think of this area right here. I'm going to revolve that area around, not the y-axis, but the x-axis. Again, on the AP test, they will tell you one or the other, so be ready for both. This is one case where you're doing around the x-axis. The way that you indicate that is you do a little loop around the x-axis and you say an arrow. If you were in physics, it would matter if you're going counterclockwise or clockwise. You have to use a right-hand rule or left-hand rule to figure out all that stuff. I'm sure Mr. Brown will love teaching you that. I still get messed up on that all the time. But anyway, you're rotating this, which means do your best to sketch this. And I spent a solid 5 minutes yesterday practicing the sketch. Hopefully I can get it correct. Because sketching things in 3D is hard in 2D unless you have skills.
You spent 5 minutes and you weren't expecting to teach the lesson today.
Yeah, I just wanted to practice. I also practiced drawing a torus, or it's T-O-R-U-S, not T-A-U-R-U-S, but a donut.
Yeah.
You want to see how to draw a donut?
Okay.
See if Mr. Sindell's skills are here. Oh, yeah, see, practice, practice, practice. So the general way that this works is to sketch this, you want to make a giant wide circle. Should I do this in blue? I should do it in maybe, yeah, I'll do it in blue. You want a giant wide open circle here, giant wide open circle here. Same thing on the back. I guess I should do it from the intersection point to make sense. Something that comes out like this, something that comes out like that. Maybe even more accurate, I remember doing this, is doing a little dashed line, and you can see it. Oh yeah, now it's three-dimensional. It should hopefully look more three-dimensional than what my last year's notes looked like. My last year's notes looked like a giant weird ball thing. This, I think, is a little bit more clear. So that is the graph, and it's this three-dimensional shape as if that area went through and was rotated around. You can think of maybe a flag rotating around a flagpole or something like that. That's what's happening. Okay, so what I'm going to do now is I'm going to take a cross-section. So I'm going to cut this perpendicular to the x-axis. Usually your cross-section will be perpendicular to whatever axis you're talking about, as long as you're doing this method. And I'm doing the disc method or the washer method, whatever you want to call it, depending if you have a hole or not. So I'm taking this cross-section right here. That's what I'm visualizing for my cross-section. My cross-section is two circles. Circle, circle. If I was cutting it at the tip here, then it would just be one circle, and it would just be infinitesimally thin, but I'm cutting it right in the half, so I get this outside. Outside is our outside, and this this inside here is our inside. So far, so good. We're able to match the cross section with the graph.
Yeah.
All right. So once we have our cross section, technically, whenever we have a cross section, those cross sections have to be three-dimensional. Right now, I have this thing that's two-dimensional. To make it three-dimensional, I need to give it thickness. So I'm going to do thickness in a different color here. Thickness. Like think of a can of soup or something. And again, if I am color coding this thing, I should make that inside red. So think of each of these slices as being thick. And of course, this thickness is going to be called what, Arrow?
D of x.
Is it d of x or d of y?
Oh. It's d of x.
It is d of x. Yeah, I'm always trying to test you, but it is d of x in this case because my cross section is going this way, so I have to actually rotate this thing 90 degrees. So yeah, it should be d of x, even though I'm drawing this thing relative to the y-axis. All right, we're comfortable on what that cross section looks like.
Okay, but why is it d of x?
Why is it d of x? Good question. So if I were taking my slices, here would be my other slice. The distance in between those slices is really the thickness of that slice. So the thickness there is in the x direction. That's a good question. And I should actually go this way. Control Shift X, Control Y. How do I undo the undos? There they are. I want to grab U and delete U to have in my final notes. All right, so moving on. How do I find the area? Again, we always come back to the idea of area. Whenever you have a three-dimensional problem, somehow simplify it to area times height. Let's look at the area. I need to think of the area of this in-between area, which is in your notes is gray, but I have color-coded notes. So this blue area right here. What's actually happening right here is I have this height. I guess I should be labeling these things now. This blue function I'm going to call f of x, which means that blue function down there is also f of x. This red function I'm going to call g of x. What is the length now? I'm talking about a radius. What is the length from the center out to the blue arrow?
Okay, if we were to label f of x and g of x on the reflected version, would it be f prime? No, it wouldn't.
It's still f of x, just rotated. Because
Because
otherwise you'll have a million f primes, an infinite number of f primes, because there are an infinite number of those functions.
Because it's a shape.
Yeah.
Okay.
It's not just two of these. There's an infinite number of those.
Yeah.
Exactly.
It's-
No. Yeah. That's a good question too.
Okay, what was your question?
So my question was, if I have a radius here, what is the length of this radius if it goes from the center on this x-axis out to the end here of this cross section? I almost gave it away there by accident. This length here is what?
The height of the outer function.
Yeah, the height of the outer function. And the outer function's name is?
F of x.
Yeah, so it's always f of x. This will change. This length here will change depending on where my slice was. If my slice was right here, it's f of x. It could be like 3. But if it's out here at the end, this circle will look much, much different. So it changes. That's why we have to describe the radius with a function, f of x. And then, of course, the inner function arrow is
G of x.
g of x. So go ahead and make a radius for the inside, radius on the inside, and that radius should be g of x. Again, it changes, so it has to be described by a function. All right, so if I come out here, then this area, this blue area in between now can be described, we're going to actually do a little bit of math now, is described as big circle minus little circle. So write that down, big circle. We'll just do no, that's not a circle, Mr. Sindel. This is a circle, big circle, and I can make this slightly thicker. I think I'm at 2 width, better. So it's a big circle minus the small circle. Color red, the smaller circle. So far, so good? All right, so what does this actually mean in terms of a formula or something that we can just memorize if we don't like thinking of it pictorially? Next side of my notes. That means I'm looking at this area. So I'm going to go out here and I'm going to say area. The area that I'm looking for. And if you want to be cool like Mr. Sindel, you don't have to be. But what I've done from last year is every time I'm talking about area, I'm always talking about what area I'm talking about, like as a subscript. So the area of this circle here. You don't have to do that. You could have just written area though. The area of that circle-y shape is equal to what? Well, I have to do the area of the big circle. What is the area of the big circle if I know that the radius is f of x?
The radius is f of x, and the function is also called f of x. So f of x is the height of the function f of x.
Yes. Yes to all of those things.
Um,
And we can even simplify it, and then we can get more specific if you want. So let's even simplify it further. If it's a big circle, we'll say big circle is big radius, so big R. We'll call this big R. And then we can say this little circle, we can, oh, I changed the color of this technology. Work with me. All right, we can call this radius big R, and we can call that radius little r. So in terms of these, instead of f of x and g of x, I can write an arrow as?
is it pi capital R squared minus can see right, but
Pi little r squared, yep.
like,
Yeah, because the area of a circle is just pi r squared. And we have different radii, so I use different variables here. And I guess if I want to be very color-coded here, I should be calling all of these other things black so I don't confuse it with the color over here. All right, so now we're going to make that a little bit more specific by using f of x and g of x. So instead of writing capital R, I'm now going to write
pi f of x squared.
Yep. So pi f of x quantity squared. And technically I'm squaring all of f of x, so if you want to be very specific, you can put brackets around f of x, or as Ben likes to do, embedded parentheses. But that whole f of x, that whole function has to be squared, which means if it was a polynomial that had two terms, or a binomial, two terms in it, you'd have to have three terms. You would get a trinomial. And that's going to be subtracting arrow.
Pi g of x squared.
There it is. Pi g of x, and then that whole g of x quantity squared. Cool, and that's basically our formula. We can actually factor out a pi out of both of these. Since they both have a pi, I'm going to factor out a pi. Now this is equal to pi on the outside times, and actually this goes with my star down here. So my star lines up, so it's pi factored out of what? What's on the inside?
F of x minus g of x squared.
Ah.
Why is it square? I don't know about that.
Yeah, so you said it as if I do f of x and then minus
So
g
does
of x.
squares have to be on the inside?
So this is how you described it squared. So, and your question is, yeah, inside or outside? And the answer is very, very important. What would you say? If you had to say one or the other, inside or outside?
Well, it's probably inside, but I thought it would be outside. But
So it has to be outside, and I can show you a way to remember that. So this thing has to be squared on the inside and squared on the inside. So if I have a numeric example, if I have,
because isn't it just distributed if it's on the inside?
let's do 4 minus
Oh, it doesn't apply to the whole f of x.
5 minus 3. Let's pretend f of x was just 5, g of x was just 3. Let's look at the difference between 5 minus 3 squared versus 5 squared minus 3 squared.
Oh.
5 minus 3, that's 2. This answer would be 4. 5 squared is 25 minus 9. 25 minus 9 is 16. So it does matter if it's on the inside or the outside.
Yeah.
And we're just following with that formula and leaving them on the inside. Cool, cool. Yeah, and then so the quicker way, if you don't like memorizing f of x and g of x because it depends on which one you label, is this. You have, and I'm going to do this all in red because, all in black, sure. This is going to be pi times top, or I think outer would actually be better. Outer squared minus inner squared instead of top minus bottom, because it depends on, I mean, generally, I don't think I've ever seen an AP test give a function that's always negative. They usually give functions that are both positive, so it's always top minus bottom. But in the rare case where they have stuff that is in the bottom, you always want to do outer minus inner. So I could have written that as top squared minus bottom squared, but that's not specific enough. And those both refer to the area of a slice. All we're doing in this section is area. So on the left-hand side here, I'm going to say this is the area of a slice, not the volume of a slice. Remember, at the very beginning, that cross-section needs to be volume. We've only found area, and you always want to start with area for any volume problem. Now we're going to turn it into volume. So go ahead and redraw volume really quickly. So the volume should look like a blue outer, a red inner. I'm doing like a side kind of view where we have some thickness. Yeah, Mr. Sindel definitely needs to work on his art skills. Okay, so the volume of one slice. How do I turn area into volume? Multiply by the height, which is dx. So tell me what to write here, arrow. You're basically rewriting this thing, but with something extra.
You put the interval in there too.
Yeah, well, not quite. just one slice would be
y times f of x squared minus g of x squared dx.
there it is. So this guy, and we can put some notes here. This guy right here, that is our area. This guy right here is our height. It's always area times height. We are always coming back to that base idea. So this would be capital B times height, I guess. Put B here in parentheses because that relates to our previous notes. So, and then you already gave this away, but to say it again, volume of all the slices, that was just one. All the slices will be same thing with the integral. Yep. So this will be copy paste. I love technology. Oh, go grab things, Mr. Sindel. Hopefully I grabbed your thing. Copy paste. That exact same thing, but with an added. Oh, I don't want to change the color. Oh no. Oh no. Turns out by grabbing everything, I was changing the color. I have to hit pen first and then take the integral of all that. From where to where?
From A to B.
Yep, because we defined that at the very beginning, our intersection from A to B. And notice that the intersection always matches with what you're rotating around. So A was on the x-axis and we're revolving around the x-axis. That means if I was rotating around the y-axis, I need points up here on the y-axis. That'll be important for later. And instead of using f of x and g of x, I'm going to do my final formula with top or outer and inner. So the area of all slices, the thing that you need to memorize most out of this entire lesson is, it's going to be, I'm going to do this all in red, sure, pi times the integral from A to B. You can, whenever you have a number, you can just factor it out. So I'm going to leave the pi on the outside. You can leave it on the inside if you want, but I like it on the outside because it looks cooler. And it's going to be outer squared minus inner squared, all of that, and dx. And again, just as a note, we'll put like a little asterisk here if you want. That dx depends on if you're rotating around the x-axis or y-axis. That's all I have. And I doubt that you have questions, but if you do have questions, now's the time. Maybe you have even more questions because you did see the lesson in advance.
No, I don't think you're more.
All right, cool. That is the entire lesson then. Go ahead and write your summary.